Okay, here we are in section 1.3, and we've learned a lot about statements and how they go together and the operators we can put between them. And we're going to kind of put all that together here on truth tables. I will note that in the folder, in the week 2 folder, there's an Excel file that just has blank truth tables on it for you to use as you work problems and practice. So I wanted to be sure that you knew that was there. You can just download it and print as many copies as you like. All right. So each statement has a truth value. It's either true or it's false. Those are the two things that can be, and it cannot be anything else. So if we're going to talk about a compound statement where we have several things going on at the same time, we have to use a truth table for that. So we're going to list all possible combinations of the statements as true or false and take a look at the resulting truth value of the compound statement under the various conditions. We can use this to distinguish valid from invalid arguments. All right, so the negation of a statement is its denial or if it's opposite, So the truth value of the negation depends on the original. A statement may be true or false, P, like that. So a statement can be true or false depending upon what case you're taking, case 1 or case 2. If P is true, then not P is false, and if P is false, then not P is true. So there's our very first truth table that has 2 columns and 3 rows. You see at the top P and not P. If you'll take a look right here, you'll see that this turned into false and this turned into true, just reversed it. Okay, so that's our very first truth table. What about a conjunction? So the value of the compound statement, the truth value, depends upon the truth values of the individual statements. So P has 2 possible truth values and Q has 2 possible truth values. So for a conjunction to be true, both of these have to be true. That's the rule. For a conjunction to be true, both of them have to be true. Remember, the conjunction is like and. So if I say A and B, then C, then both of those have to be true for the resultant statement to be true. So here I go with my second truth table. I'm just going to go ahead and set it up, P and Q. And true, false, true, and all those sorts of things there. So I've given, notice right here, P, true, true, false, false. Now why did I use 2 here? Because as I begin to compare more and more statements together, I have to get a possibility for each possible value of the original statement. So the way I do this is if I have 2, that means I'm going to have 2 times 2 or 4 rows past the label row up here. So I just do TTFF, 2 and 2, and then alternate, TFTF. Okay. So P and Q, remember, both have to be true for the statement to be true. So there it is, true, but in every other instance it's false, because at least one of the 2 truth values of the statement is false. Okay? What about a disjunction? Now that depends once again on the individual statements, and each of those has 2 values. Now for the or, either or both must be true for it to be true. So one of them can be false. The only case in which the statement is false is when both are false. So here's the table I had from before. Okay, so now P or Q. So if either one of them is true, the statement is true. That makes sense, both true. Okay, P is true here, so it's true. Q is true here, even though the other is false, so it's true. The only case in which it is false is when both are false once again. So let's take a look here and work kind of a problem. Under what specific conditions is the following compound statement true? Under what specific conditions is it true? I have a high school diploma, or I have a full-time job and no high school diploma. So this is a compound statement. We have to express it in symbolic form. We're going to define P and Q as I have a high school diploma is P and I have a full-time job is Q. Okay. So here's our given statement. P or Q and not P. Okay. We learned how to write those in the last chapter, but that is the compound statement. So I have two letters, so that requires a 2x2 truth table with 4 rows past the label rows. So we're going to go ahead and get columns for each statement and a column for each expression, for each connective in the expression. Disjunction, a conjunction, and a negation. So we're going to need columns for all of those. So we have 2 columns for P and Q, and then 3 more columns for our connectives. So we need 5 columns in total. Okay, so here we go. So P and Q, T and T, when they're both true, well, when P is true, not P is false, right? And when P is true, when P is false, not T is true. Okay, so we filled out that column. Now let's go to this column right here. So we're going to be comparing Q and P. Okay, Q and P. So we know for and here, the conjunction, both have to be true for it to be true. So let's check. TF, false. The next one is FF, false. The next one is TT. That's true. The next one is FT, so that's false. Okay, good. So we've done half of our conjunction, and now we have to use P or this column right here. So we're comparing those columns together using or. Now remember for or, either can be true. So let's see here. We've got T, F. So since it's an or, that's a true. We have T and F, true. F and T, true. F and F, that's the only case in which it is false. So our statement, I have a high school diploma or I have a full-time job and no high school diploma, is true in every case except when the speaker has no high school diploma and no full-time job, when both of these original statements are false. Every other time the statement is true. But if these are our initial truth conditions right down here, that makes the entire logical statement false. So that's how we will begin to pick this apart. What about the disjunction? So if compound statement has 2 different letters, 2 times 2, how many rows are required if a compound statement consists of 3 letters? Each statement has 2 truth values, T and F, so we have to contain 8 rows to account for all of the possibilities. So in general, each time we add a row, we basically double the number of rows that are needed. A new statement, we double the number of rows that are needed. So remember, a conditional statement is if P, then Q, and P arrow Q is how we symbolize it. If you give me $50, then I will give you a ticket to the ballet. Okay, if you give me $50, then I will give you a ticket to the ballet. So P is you give me $50, and Q is I give you a ticket to the ballet. Those are the 2 possibilities here. So P then Q, if you give me $50, then I will give you a ticket to the ballet. So we can view this conditional as a promise. Suppose that you give me $50. That is, let's just suppose that P is true. I can do 2 things. I can give you a ticket, which would make Q true, or I can not give you a ticket, which would make Q false. Okay? So when is the statement true. If I do give you the ticket, the conditional P then Q is true. If I don't, then P then Q is false. Okay? So the only time a conditional is going to be false, once again, as we said before, is if the hypothesis is true and the conclusion is false. Okay? But what happens if the hypothesis is false? What about the truth value here? We don't really have a way to define this, do we? Let's say that you didn't give me $50. I could either give you a ticket or not give you a ticket, making Q true or false, but what would the value of the entire statement be? Well, let's say that you do not give me $50. P is false. Okay? If I do not give you a ticket, then if then is not false. If I do not give you a ticket, then if then is not false. When is the only time that an if then statement is true or is false? It's only true if the premise is true and the conclusion is false. Now we have to have a binary, a true or false value for every statement. Since the statement that I gave you can be either true or false, you don't give me $50 and I give you a ticket or not, it's not false, so it has to be true because there are only two things that it can be. If I did give you a ticket, then it is also not false and must be true. So if the premise P of a conditional is false, it doesn't matter what the conclusion is. If the premise of P is false, it doesn't matter what Q is, it's always true. The entire statement is always true. It's automatically true because it is not false. So here's the truth table that would define that. The only time this conditional statement right here is false is what? When the premise is true but the conclusion is false. In all other cases, it's true. In all other cases, it's true. So under what conditions is this symbolic expression true? So our truth table has two rows, and it contains not P, and then Q, then not P. Okay? So there's our row right there. So we have these columns that we need. So TT, TF, FT, all the possibilities between P and Q. So I'll go ahead and fill in the not P thing here. And then we're going to be doing Q, then not P. So these columns together in this order right here. So true, false. For conditional, that's false. Everything else is true. Okay? When you purchase a car, the car is either new or used. If a salesperson told you it is not the case that the car is not new. That might be kind of a silly way to phrase that, but let's work our way through it. What condition would the car be in? Okay, the compound statements consist of one statement. P, the car is new, and two negations. It is not the case that the car is new, and the car is not new. Okay? So we need two truth tables, two rows, and now we have the two linker columns, not and then not, basically. So we'll go ahead and fill in not P, and then we'll fill in not P. So basically, given this column right here, we just reversed the truth value of the items in that column and put them in this column right here. So that kind of leads us to the conclusion that not P is really P. Okay? So it's just like in math, if you multiply -1 times -1, it's +1.
Hi, Dad.
So doubling up on the nots just reverses the value of the previous one. Since there's only two values, true or false, you just swap back and forth. We call this situation in which the truth values are exactly the same for two particular columns in every single row, we call that equivalence. P is equivalent to not P. So the car is new is equivalent to it is not the case that the car is not new. See how that worked out? So we can use these interchangeably when we want to. So, equivalent expressions, as I said before, are symbolic expressions that have identical truth values in each entry. So the expression P is equivalent to Q there is indicated by that triple equal sign. Consider, if I'm taxes. So the two compound statements become, if I am a homeowner, then I pay property taxes, P then Q. And if I am a homeowner, I do not pay property taxes, P and not Q. Those are our two possibilities. So let's go ahead and start working with our truth table. I have two letters, so I've gone ahead and filled that out as we always do. I'm going to go ahead and do not Q because that's our first connector. And then we have P and not Q to check out the truth value of that based on what's in the previous columns. And then we have P then Q to check out what's in the previous columns. So we're basically going to see if we end up with the same values in each of these two columns in every position. Okay, so I'll go ahead and fill out the not Q, which is easy to do. And now we're going to work on the P and not Q. So we have P and not Q. So since Q is false, that makes it false. And then on the next one we have P and not Q, both are true, so that's true. P is false, not Q is false, so that's false. P is false and not Q is true, so that makes that false. Very straightforward. Now P then Q should be very easy for us to fill out. When is the only time this is false? The only time it's false is when the premise is true and the conclusion is false. So all of those are true except for that. Now these two compound statements are not equivalent to one another. Notice that they differ in the position. They differ in the position based on the values in the truth table. Okay, they're very different. But they are exact opposites. Whatever this is, that is the opposite. So the two columns are opposite one another. Okay, that's a very important thing to note. They're exact opposites of one another. So one of these is the negation of the other. One is the negation of the other. So if you want to put it that way, we say P then Q is equivalent to the negation of P and not Q, right there. That's exactly what we derive from this column up here to get this expression right here that's equivalent. Now in mathematics and so forth, when we have equivalent statements, that's very useful because we can rewrite things in different forms. So the negation of a negation is equal to the original statement. So not P is equal to P or equivalent to P. We discovered this negation formula in our last problem together there. So are there other formulas that we can learn? Well, thankfully there are. The English mathematician and logician Augustus De Morgan came up with a whole bunch of these, and these are the first two of the De Morgan's laws. And we'll pick up some more of these as we go along. So these are some of the laws that we can use to put things together. So let's take a look at this little problem. Using De Morgan's laws, find the negation of each of the following. It is Friday and I receive a paycheck. Okay, that's F for Friday and that's P for paycheck. So F and P, that is our expression. So what would happen if I negated that? Well, according to De Morgan's law, if I negate a conjunction, I end up with the negation of each of the members of the conjunction in a disjunction. So that would be translated back as it is not Friday or I did not receive a paycheck. Okay, that's how that would be stated back. So this is just a relationship. Once you have it, you can work with it. I encourage you to do your best to work your way through all of these. The only way to learn this kind of thing is just straightforward drill and practice. Okay, so get out some of those truth tables I gave you and just churn through them. It's the best thing that you can do. All right, thanks very much. And I have worked these out and I have put them online as the solutions to these problems.